Hi, my name is Bahadur Ahmedov. In this video lecture, we are going to discuss about diagonalization of symmetric matrices. If you remember previously, we talked about factorization of a matrix into its eigenvectors and eigenvalue matrices. So essentially, a matrix can be written as a multiplication of the x times to the lambda times to the x inverse, where x is going to contain its eigenvectors and lambda is going to contain its eigenvalues. And this decomposition is going to be called as the diagonalization in general. And please note, so this is going to be called as diagonalization. So please note that certain type of the matrices only have the diagonalization. So essentially, diagonalization is possible if all of the eigenvalues of matrices are distinct, are different from each other. In this lecture, we are going to discuss about diagonalization of a matrix if this A is the spatial type of the matrix, or essentially it is the symmetric matrix. So let's discuss what is the symmetric matrix and let's define this. So if you're given some matrix S with, for example, 3 by 3 matrix with 9 entries, then it is called symmetric over this diagonal. So if all of the entries above this diagonal and below the diagonal are going to be the same in the corresponding positions. For example, this entry S1, 2 and this entry S2, 1 are going to be equal. So this entry S1, 3 is going to be equal with the S3, 1. And this entry with the S2, 3 is going to be the same as the S3, 2. So this matrix is going to be called as symmetric if the corresponding entries below and above the diagonal are going to be the same. So let me give you some examples. So let's say S is given as 1, 2, 3, 4, 5, 6. Then this entry here is going to be equal to the 2, this entry is going to be equal to the 3, and this entry is going to be equal to the 5. You see, so this entry here and here are the same. Here and here are the same, and here are the same. So let's discuss how we can identify mathematically whether the matrix is symmetric or no. So you see, so this entry here, S1, 2, is the same as the entry S2, 1. So how we can get the entry S1, 2 from the S2, 1? So obviously by transposing the matrices. So if you transpose the S matrix here, so let's transpose this matrix. So it is essentially when you just copy the first row as the first column, it's going to be 1, 2, 3. And the second row is going to be copied as the second column. It's going to be 2, 4, 5. And the third row is going to be copied as the third column. It's going to be 3, 5, and 6. And you can see here that they are the same. So that's going to be the definition of a symmetric matrix. I mean, not the definition, it is how we are going to identify whether the matrix is symmetric or not by just checking equality of the matrix into its transpose. So the definition of a symmetric matrix, so definition. So the let S is, so, or let's call this like S is a symmetric matrix if Sij is going to be equal to the Sji for any I and j which are not equal. So this is going to be the definition of the symmetric matrix. And how we can identify the symmetric matrix is by taking the derivative, by taking the transpose of the matrix S and equalizing this to the S. So if they are equal, that means that they are symmetric. So now let's discuss about the diagonalization of symmetric matrices. So let's assume that S has a diagonalization. So it essentially has, it can be written as the X times to the lambda times to the X inverse. So at the same time, let's transpose all of this part, all of the two parts of this equation. So essentially here on the left hand side, I will get S transpose. On the right hand side, it's going to be X lambda X inverse and its transpose. And if you remember, when you are going to multiply the three matrices or two matrices and transpose this, you can open the brackets. You can multiply this to the transposition of the matrices separately, but in reverse order. So they have to be multiplied in reverse order. So we can multiply the x inverse transpose first, then the lambda transpose. So the lambda transpose is going to be the same as the lambda because the lambda is a diagonal matrix, and the x transpose here. So since S is a symmetric matrix, then you can write this down that this S is equal to S transpose. So that's why the right hand side of this equation is going to be the same as the right hand side of this equation. So it's going to be x lambda x my inverse is equal to the x inverse and transpose lambda and x transpose, right? Okay, so it is kind of clear for us from here that from this two equation that x inverse is going to be equal to the x transpose. So from here we can write this down that x inverse is going to be equal to the x transpose, or essentially x transpose times the x is going to be equal to the identity because the x transpose is the inverse of the x. So this is the beauty of the diagonalization of the symmetric matrices, because in order to find the inverse of the matrix with the eigenvectors, we just need to transpose this. And if you remember, this type of the matrices, when the inverse of the matrix is equal to its transpose, are going to be called as an orthogonal matrices. So they are called as orthogonal matrices. So let me remind you what is the definition of an orthogonal matrix. We usually denote the orthogonal matrix as a Q, capital Q. A matrix Q is orthogonal if its columns are orthonormal. So if you remember, orthonormality means that the columns of this matrix Q are all unit vectors and they are perpendicular to each other at the same time. So let's assume that Q is going to have n columns, Q1, Q2, and so on, Qn. That if you multiply the Qi transpose to the Qj, and this is going to be equal to so if you scalarly multiply the Qi to the Qj, it's going to be equal to the 0 if I is not equal to the j, and it's going to be equal to the 1 if I is equal to the j. So essentially, if you multiply a vector to itself, you're going to get 1 because all of them are the unit vectors. And if you multiply a vector, essentially the column of the orthogonal matrix, into another column, you're going to get 0. So this is what is called as an orthogonal matrix. And for any orthogonal matrix, the Q transpose is a Q, or Q to the Q transpose is going to be equal to the identity. So the inverse of an orthogonal matrix is equal to the transpose of the Q. I mean, it's, of course, if the Q is a square matrix. So if so let's do an example with orthogonal matrices. So try to understand a little bit more deeper what does it mean that the matrix is orthogonal matrix. So let's say you are given a matrix A with the columns -1, 1, 1, and 1. So could you please tell me whether this matrix A is orthogonal? Well, so I've got the two columns, so let me denote the first column of the matrix A as a C1, with the entries -1 and 1, and the C2 is going to be equal to the 1 and 1. If you multiply the C1 to the C2 as a scalar multiplication, it's going to be -1, 1 times to the 1 and 1. Obviously, it's going to be equal to the 0. So it means that they are perpendicular. But at the same time, this matrix A is not orthogonal. It's not orthogonal. The reason is that the columns of this matrix A are not unit. So we can get an orthogonal matrix from this A by just normalizing its columns. So if you just divide the first column C1 into its norm, so it's going to be a -1 and 1, and the norm of this matrix is going to be simply 1 divided to the square root of 2, so simply square root of 2. And this is going to be the first column of the orthogonal matrix, so it's going to be, let's denote this as a Q1. And the Q2, the second column, is going to be C2 divided to the norm of the C2, which is going to be equal to the 1 over square root of 2, 1 and 1. So let me just write down what does it mean, the norm of the C1. C1 is going to be -1, the first component of the C1 in the square, plus 1 in the square from the square root, which is going to be square root of 2. And the same is true for the C2. So the C2 is going to be 1 in the square plus 1 in the square from the square root of 2. It's going to be square root of 2. Okay. So these two columns, Q1 and Q2, are going to be the columns of the orthogonal matrix. So the Q is going to be -1 divided to the square root of 2, 1 divided to the square root of 2, 1 divided to the square root of 2, and 1 divided to the square root of 2. And that's the orthogonal matrix. So this is the orthogonal matrix. Because its columns are orthonormal. Well, now let's just multiply the Q transpose to the Q, or Q2 to the Q transpose. It's going to be, so let me transpose this matrix first of all. If you transpose, essentially you're going to get the same matrix. And if you multiply this to the Q, -1 over square root of 2, 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, what we obtain is the following matrix. So the first row is going to be multiplied to the first column. It's going to be equal to the 1. The first row to the second column is going to give you 0. The second row to the first column is going to be 0. And the second row to the second column is going to be equal to the 1. So you see, so we multiply the Q transpose to the Q, and we've got the identity. So on the inverse matrices, the multiplication of the inverse matrices is going to give us the identity. So that's why the Q transpose is going to be the inverse. So if you're given a Q, in order to find its inverse, just transpose this. So that's the beauty of orthogonal matrices. So now let's go back to the diagonalization of a symmetric matrix. So in order to demonstrate how to build the diagonalization of a symmetric matrix, let's do an example. So let's do an example of the diagonalization of a symmetric matrix. So let's say you are given a matrix S with the entries 1, 2, 2, 4, and we need to find its diagonalization. So essentially, it's going to be Q lambda and the Q transpose. So instead of writing down as a Q inverse, we're going to write it as a Q transpose. So in order to find its diagonalization, we need to perform the following operations. First of all, we're going to find the eigenvalues of this matrix. So find the eigenvalues, and we need to construct this matrix lambda. Second step, we are going to find its eigenvectors. So find the eigenvectors of this matrix S. So let me denote the eigenvectors as, let's say, C1 and C2. So I'm not going to put them as the columns of the Q, because the columns of the Q are going to be, so these two eigenvectors are going to be orthogonal matrix, because this S is the symmetric matrix. But they're not orthonormal, so we need to normalize them. So the S is going to be divided to the S1, and the Q2 is going to be S2 divided to the norm of the S2, and that's going to create the matrix Q. And that's it. So this is essentially how we're going to construct the diagonalization of a symmetric matrix. So let's start from the first one. So we are given the matrix 1, 2, 2, 4. In order to find the eigenvalues of this matrix S, what we can do is we can solve this equation. Determinant of the S minus lambda I is equal to the 0. So let's do this. So it's going to be 1 minus lambda, 2, 2, 4 minus lambda. So please note that this is S minus lambda I matrix. So we have to find its determinant and equalize this to the 0. So if you find a determinant, it's going to be equal to lambda minus 1 times the lambda minus 4 minus 4. So if you open the brackets up, it's going to be lambda in the square minus 5 lambda plus 4 minus 4 is equal to the 0. So if you take out so this 4 and 4 are going to be cancelled out. And if you take out the lambda out of the brackets, you're going to get this equation, which is clear that the lambda 1 is equal to the 0 and the lambda 2 is equal to the 5, or vice versa. So we're going to create this matrix lambda with the entries 5, 0, 0, 0. Now, in the step number 2, we're going to find the eigenvectors of this matrix S. And if you remember, in order to find the eigenvectors, we need to just construct this matrix S minus lambda I. And we need to find this vector S1, let's say, so that this multiplication of this matrix to this vector is going to give you the 0 vector. So in this case, this matrix is going to have the determinant to be equal to the 0. So the determinant of this matrix is equal to the 0. So this is how we choose this lambda, so the determinant is going to be equal to the 0. So it means that there are infinitely many these vectors S1, which is going to make this multiplication to be equal to the 0. So essentially, we are going to just find one, and then we're going to just normalize this. We're going to make the length of this S1 to be equal to the 1 in order to create the Q matrix. So let's first of all find the S1. So S matrix, if you remember, was 1, 2, 2, 4 minus lambda 1. So I'm going to do this for the lambda 1, which is equal to the 5. So the lambda 1 times the identity, which is 1, 0, 0, 1. So let me just substitute here lambda 1 to be equal to the 5 immediately. So it means that we need to subtract the 5 from the diagonal entries of this matrix, which is going to be equal to the minus 4, 2, 2, minus 1. We need to bring this matrix into zero echelon form. We can do this by just multiplying the first root as a 1 over 2 and adding this as a second. We'll obtain minus 4, 2, 0, and 0. Well, see, so the second column here is the free column. So we always set the variable which will correspond to the free column to be equal to the 1. And then we are going to solve this equation. So the first equation tells me that minus 4 times the x1 plus 2 times the x2 is equal to the 0. If we substitute x2 to be equal to the 1, we'll obtain that minus 4x1 plus 2 is equal to the 0. And from here, it's clear that x1 should be equal to 1 over 2. Well, if you substitute 1 over 2 instead of x1, it's going to be minus 2 plus 2, which is equal to the 0. Well, the first eigenvector is going to be equal to 1 over 2 and 1. But again, you can take this eigenvector with any length. So you can just simply multiply this as a 2. It's going to be, or for example, or we can take the S1 to be equal to the 1 and 2 vector as well. It doesn't really matter because still, so this vector S1, if you substitute 1 over 2 and 1 or 1 and 2, it doesn't matter. This is going to make this multiplication to be equal to the 0, and that's the important point. So this is why we need S1. So we need S1 so that the multiplication of this matrix into the S1 is going to be equal to the 0 vector. So let's do the same thing for the lambda 2, which is equal to the 0. So S matrix is equal to, so S minus lambda I. So since lambda is equal to the 0, it's going to be simply S. So the S matrix was 1, 2, 2, 4. We need to bring this to the row echelon form by just multiplying the first row to the minus 2 and adding this to the second. We will obtain this. It's going to be a 1, 2, 0, and 0. And again, we are going to set the second column or the second variable to be equal to the 1 because it's free. So the x2 to be equal to the 1. And then we're going to solve this equation, which is 1 x1 times the 1 plus 2 times the x2 is equal to the 0. If you substitute x2 to be equal to the 1, it's clear that x1 is going to be equal to the minus 2. Well, the second eigenvector is going to be equal to minus 2 and 1. And again, we choose this vector as minus 2 and 1 because if you multiply minus 2 and 1 into this matrix, right, or this matrix, it's going to be equal to the 0 vector. So that's the reason why we choose this vector, or the second eigenvector, to be equal to the minus 2 and 1. Well, in the third step, we need to obtain the columns of the Q. So the Q1 is going to be obtained by just normalizing C1. So C1 divided to its norm. Okay, so if you remember C1 to be equal to 1 and 2, well, the norm of the C1 is going to be equal to the square root of 1 in the square plus 2 in the square, which is going to be equal to the square root of 5. So I'm just going to put everything down to here in order to get this vector with the components 1 and 2 times the square root of 5. At the same time, Q2 is going to be equal to the C2 divided to the norm of the C2. So again, if you remember, C2 is equal to this metric, to this vector, minus 2 and 1, minus 2 and 1, and the norm of the C2 is going to be equal to the minus 2 in the square plus 1 in the square. Well, it's going to be equal to the square root of 5 again. So the Q2 is going to be equal to the 1 over square root of 5 minus 2 and 1. So in total, in general, we're going to get this Q matrix to be equal to the 1 divided to the square root of 5. So we need to put the Q1 as the first column, so which is going to be equal to this vector, 1 and 2, 1 and 2. And the second column is going to be equal to the minus 2 and 1. Well, so this Q is orthogonal matrix because if you multiply the Q to the Q transpose is going to be equal to the identity. So that's why the inverse of the Q is going to be simply transpose of the Q. It's going to be 1 divided to the square root of 5. So I'm just going to write down the first row as the first column. It's going to be 1 and minus 2. The second row is going to be written as the second column. It's going to be 2 and 1, and that's going to be the Q transpose. So our matrix S, symmetric matrix S, with the components 1, 2, 2, 4, can be written as the multiplication of the Q lambda and the Q transpose, where the Q is equal to 1 divided to the square root of 5, 1 and 2, 1, 2, minus 2 and 1, right? Multiply to the lambda was the entries 5, 0, 0, 0. Multiply to the transpose of this Q, which is going to be equal to the 1 divided to the square root of 5, 1 minus 2, 2 and 1. Essentially, if you multiply the three matrices, we are going to get this as original matrix. So that's how we are going to diagonalize the symmetric matrices. And the beauty of the diagonalization of the symmetric matrix is that if you find a matrix with the eigenvectors, in order to find its inverse, we just need to transpose this. So by just making sure that the columns are orthonormal. So in our next video lectures, we're going to discuss about so-called singular value decomposition. That is when, if you're given a matrix which is not symmetric, not square, how to still find the diagonalization of those kind of matrices using some features of the diagonalization of symmetric matrices. So thank you very much for your attention. I hope that this video was helpful for you.